Hello everybody, Dr. Ismaili talking about regression analysis, and that's probably one of the earliest predictive methods that people started thinking about. Okay, let's jump into it and look at the regression. What is regression with one example? Imagine this data set is about the price of a house, and we know some inputs about each house, like crime rate, the location that the house is located, the room size, age of the house, and the tax paid on that property. And based on these, there is a price associated with that house or that property. And we have many of these samples for different properties. And now the goal is to see if we can predict for the new house what is the fair price. We call this is a regression problem because we are predicting continuous values, not categorical value. Categorical values are discrete classes that sometimes we are interested in. Say we want to predict if the stock is gonna raise or fall down tomorrow. Other examples of regression you're gonna see when you wanna predict the salary based on occupation, education, work experience, and so on. Or you wanna predict the pollution with the engine size of the car, year of the car, make, model, and so on. Or sales based on age, education, work experience of the person. So you want to predict how much he can sell. And weather based on what time of the day we are talking about, and which month we are in, and the location, and other predictors. So if you look at these y variables, we are predicting continuous values. So that's one of the things that you're gonna distinguish regression problem from the classification problem. In the classification we're gonna talk about later, but you wanna predict which class the new observation belongs to. But in regression, we wanna predict what is the continuous value for this particular observation based on input features. Input features can be categorical or continuous values, but the output is a continuous value. So let's practice. Which one do you think is a regression problem? Predicting normal versus abnormal, predicting if the stock will rise or fall, grouping similar cars, predicting stock price for tomorrow. So if you think about it, only number 4 you're predicting the continuous values. Number 1 is a binary classification. You want to say yay or nay for normal and abnormal. Predicting if a stock will rise or fall, again, it's a binary classification. You want to say yes or no, 0 or 1. And grouping similar cars, you can have 4, 5, 10 classes of cars, and you want to assign new car to any of those classes. So it's a classification problem. Regression algorithms, there are many of them. We're going to cover a few of them in this course, in particular linear and polynomial, which are commonly used in the industry. What is our goal? Say in the previous example, we have a bunch of houses, and we know their price and other features. So we want to feed that to a learning algorithm, and that learning algorithm is going to learn a function. This function, we're going to call it hypothesis function, which is a function of theta and input features. And for new house, if we know this magic box in the middle, hypothesis function, for the new house, we know what is the features, and that's how this magic box is gonna estimate the price of the house. So learning algorithm outputs a function called hypotheses in this example. This hypothesis function is going to be with us for many different machine learning or predictive algorithms. The goal is to find that magic box or hypothesis function, which is a function of theta. And you're going to see later that all our effort is to find that best theta or fit that theta. And that parameter is going to determine how bad or good your magic box is. Okay, first method is to use linear regression, and what it means is hypothesis function h is going to be a linear function of those thetas and observation x1. And now again, the goal is to find these theta 0 and theta 1. So imagine you have observations like this. X-axis is number of rooms, and that's the only thing that you know, for example, for determining the price of the house. And now imagine this blue line is the best line or the first initial guess to relate number of rooms to price of the house. Now if we look at the point like this, we know that the actual price is a bit below 5.5 times million, but our blue line is gonna estimate it like a bit more than 6 million, right? So there is error, and error is like this, and our goal in this course is to minimize this error. So of course, with linear line, there is so much that we can do because there is no way to fit all of these lines and still have zero error. To do that, you need nonlinear lines or hyperplanes in higher dimensions, but in this course anyway, we're gonna find this minimum error, or we're gonna find theta 0 up to any dimension that you have, in a way that we're gonna minimize this error. So formally, the problem is to find these thetas such that mean square error gets minimized for all training samples. And if that happens, we are hopeful for the future samples, which we don't have, we're gonna have also good predictions, because if you do for good for the past, hopefully you're gonna do good for the future. So formally, this is a minimization problem, and the goal is to minimize a difference, and that difference is the one that your model or your magic box or that h function predicts with the real y's. And again, these are for all i's or all observations in the past. That's why the summation is from I equal to 1 to m, which m is the number of observations. And we wanna sum all errors, in fact squared errors, because sometimes we overestimate, sometimes we underestimate. So sometimes h is more than y, sometimes it's less than y, and these negative and positive numbers, if we don't square them, they're gonna cancel out each other, and they're not gonna give us a realistic view of error. And this m is to divide it to give sense of mean of these errors, and number 2 here is just for mathematical convenience. Also, we call this function as cost function, we're gonna see this over and over. For different algorithms, we're gonna define this cost function. Probably it's gonna be a bit different from this one, obviously, but the meaning is gonna be the same, which shows the difference between real numbers and our predictions. All right, so we saw two important functions, hypotheses and cost function, and our goal was to minimize this cost function. So let's visualize this cost function, and to do that, let's assume that theta 0 is 0. We don't have the constant term here, just to make it simple. H is just a function of theta 1 and x1, which is going to give us a linear line if you plot this h versus x1. So this is going to be a line which is crossing the origin. You don't have constant term to go positive or negative. Now imagine we have 3 points that we have observed in the past. We call them training set. This could be 3 houses that you know the number of rooms and corresponding prices for their houses. So if you imagine this theta 0 is 0 and this theta 1 is equal to 1, then this function, if you plot it, it's going to be this green line. Now, if you look at the cost and you calculate these differences, you're going to see that, for example, when you were in 1, your real output, or the y, was 1, and your estimation, which is coming from this green line, is going to be also 1. So 1 minus 1 squared plus, these are the error terms, right? For the second observation, the real number or real past observation was 2, and your estimation based on this green line is also 2. So 2 minus 2, and also 3 minus 3 for the next observation. So if you add these terms and use that equation, you're gonna see that the cost is 0. So if we plot this cost function versus theta 1, when theta 1 was 1, the cost was 0. So we have this point here. Now imagine our theta 1 is also 0. So theta 0 is 0 and theta 1 is also 0. So this equation, if you look at this, is going to be h equal to 0. 0 plus 0 times something. So h is equal to 0. We know that is what that is. That's this green line, horizontal green line. And now let's look at the errors. So when you are at 1, your real output is 1, but you're estimating as 0 because the green line says 0. So 0 minus 1. Here, your real number is 2. You're again estimating it as 0. So 0 minus 2. And here also, real number 3 minus 0. So if you add these error terms, it's going to be 2.3. And it's not 0 anymore. So when your theta 1 is equal to 0, your cost function is a non-zero like this. Also, say this time if we have theta 1 is equal to 2, and still we keep theta 0 for simplicity as 0. If you do the math again, now this time you are overestimating, and these error terms are gonna add to another number, which this time is similar to the previous one, 2.3. And if you plot that, it's gonna be here when your theta 1 is equal to 2 you're gonna have another cost, non-zero cost. And remember that we don't like these costs because they show the difference between theta 0 and theta 1. And if you put so many numbers, you're gonna have a curve like this, which shows your cost function is minimum at one point, which is theta 1 equal to 1. That's why we call it optimal point for cost function, which is corresponding to your best or optimal theta 0 or theta 1. So remember, our goal was to find this whole magic box, and what we had to do was to find optimal theta 0 and theta 1. So to finding these theta 1s, we introduced a cost function, and this theta should be revised, but this cost function is minimum at some point, which corresponds to optimal theta 0 and theta 1, which we saw that. But how we find that mathematically? We just saw that graphically, and we tried a bunch of points, but what is the good programmatic way of calculating these theta 0, theta 1, theta 2? Well, gradient descent is one of the simple and very effective methods to solve these type of optimization problems. And let's look at it visually first, and then we can talk about equations too. Say you have a cost function like this in 3D, and you want to find the minimum cost in this graph. Now if you randomly start from a point like this and look 360 degree around yourself and decide which direction is the easiest way to go downhill. So you don't have to know everything about all the passes, all the things in the future, just small and baby step around yourself. And if you decide that and take action, so you take this small step, and then again you spin and look around yourself where you want to go. Maybe this time it's this direction, and if you keep going like this, you're gonna end up at some local minimum. But imagine you your starting point was here, and you took those steps. You could end up to another local minimum, which is interesting property of non-convex problems, which they have different local minimums, and gradient descent. If you start from different locations, you may find different local minimums. But in convex problem, you only have one local and global minimum. This is an optimization topic, but it is really nice if we can define this J function in a way that it is convex optimization problem, and there is guarantee to find one optimum location, which is global. So you're not going to have several local optimization, and we are able to do that in many algorithms. We can define, or we can change the equation in a way that it is not convex in one form, but you can convert it to a convex problem. This walking downhill can be formulated as these two equations. It's going to be similar equation for other variables. If you have more than two variable or parameter, it's going to be same approach. So what it says is you want to replace, this is the symbol of replacing the old theta 0 with the new one. So this new one is the old parameter minus something. So this minus something is going to be similar, and it's gradient with respect to the parameter that you're talking about. So if it is this equation, theta 1 is going to be updated with respect to theta 1, and so on. So what it means is basically, say, theta 0 minus in the direction that your gradient is going to be descended, or it's going to be reduced. So because you want to walk downhill, that means if, say, this term is negative, negatives times negative is going to be positive, so your theta is going to grow. And what it means if your slope, which is this term, we know that from calculus. So if the slope is negative, negative times negative, it's going to increase the theta, which means keep going, right? But if it is positive, which means uphill, you are going in the uphill direction, which is not good, because we want to go downhill. We want to find the minimum, not the maximum. And if it is positive, minus positive, it means you are decreasing your theta, which means go back. You are in wrong direction. That is same for all other variables. So you're gonna repeat this process for all of your thetas, and you're gonna find the global minimum or local minimum. So this process can be done in two ways. One is correct, one is not correct. The first one is you find these temporary parameter update for both of them, or if you have many, for all of them, and then update them at once. So do not find the first one and update the first one and move on to the next one. This is not correct, because when you update the first one, that's going to affect your second derivative in here. And you don't want to do that, because you don't want to partially update. You want to find everything like this at first, and then update everything at once. Okay, so this process is gonna find the good thetas for us, and we've seen that these good thetas are gonna create good magic box or hypothesis function that we already talked about, and that magic box is gonna predict based on any inputs that you're gonna have for new observations. It's gonna predict the future, or predict the price of house, or predict the temperature for tomorrow, any problem that you're solving for. Alright, now it's a good time to go to the coding section. So let's move on to the next video, and I'll talk about how scikit-learn implements linear regression or other regression methods.